Go.
Interesting things happen when things turn. Let's explore this.
I like it. Woohoo!
Oh, we forgot to put it in go mode. Alright. We'll start with this. Keep it simple.
There are many things that turn. That clock is turning.
So do this now. Make two fractions from this equation.
You guys know how to do that? On your mark, set, go!
Do it. 12 eggs over 1 dozen. And then the other option is 1 dozen over 12 eggs.
Simple, yes?
Yes, very simple. Miss Moore has 156 students who will work in pairs on the egg drop challenge. Dun 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 dun. How many dozen eggs must she buy?
Well, first of all, if they're working in pairs, how many eggs are they going to need?
Okay, if they're working in pairs, 156 divided by 2, that gets me 78 pairs, right?
Yes. Hey, Rolando, take a picture of us with your phone, would you?
Which also means that we're gonna have to buy 78 eggs, right?
Close.
Okay. So if I have 78 eggs, how many dozen eggs must I buy? Okay, well,
Email that to her.
I've got eggs up here. I want to figure out dozen. I'm gonna put eggs on the bottom over here, and 1 dozen up top because we want these to cancel out, right?
Yep.
Cancel, cancel. 78 divided by 12 is, can't do that one in my head.
Me either.
78 divided by 12, and I get 6.5. So technically that's 6.5, but how many dozen eggs am I have to buy? 7 dozen.
You're going to use 6.5, and you'll have how many eggs left over? 6.
6.
Woohoo!
Woo, that's it. Okay. So we just used our different conversions to go from one thing to another.
That's an important skill, and it will get you through chemistry.
It sure will. Moles. Okay. If a stopper twirled on a 0.7 meter string goes around once in 0.48 seconds, what can we know?
Well, there's a bunch of stuff you can get out of that.
What were those equations for circular motion?
Well, let's see. If the string is 0.75 meters, that's the radius, yes? And if we know the radius and nothing else, what else can we know?
Well, we can know the velocity, because velocity is 2 pi r over t.
Yep,
right?
we can know the velocity. We could also know the circumference. So that would be that 2 pi r is the
Right.
circumference.
Because we've got the radius. Okay, so we know the circumference. We know the velocity because we've got the radius and we've got the period.
And since that velocity, the direction of the velocity is constantly changing, that's an acceleration.
Mm-hmm.
Sweet.
So once we get the velocity, we've got the radius, we can also find the acceleration. Dang! We can find a lot of things. We can know a lot of things. Okay, 60 RPMs means 60 revolutions per minute. What would be the period?
The question is, what the deuce does period mean?
What the heck is a period?
That's the time for one revolution.
Okay,
I think you got that
Oh,
upside down.
I do.
Yeah,
Revolutions per second, right? Or no, sorry.
you could just put revolutions over seconds. There you
Okay.
go.
And think back to when we were doing what was it? Gravitational motion with the satellite and the stuff, right?
Yep, yep.
And we had to convert that hours into seconds. When
Right.
we're talking about period, we're talking about seconds always.
Unless they give you a separate thing, but in almost all cases, it'll be seconds.
So if we have 60 revolutions in, what is it, 1 minute?
Yeah. So we can make an equation out of 1 minute is how many seconds?
How many seconds are in a minute? 1 minute is
60 seconds.
60 seconds.
That's right.
So 60 divided by, these cancel, revolution per second, that's what we want. 60 divided by 60 is just 1. Oop. Okay,
Revolution per
revolutions,
second.
seconds, divide, we're good.
Boom, boom, boom.
Okay, so our period would be 1 revolution per second.
That's a simple example of something that you... Oh, we have an example of this over here.
Oh, sweet. Okay, here we go. So it says We're like walking away. It says,
We're both walking
we're
away.
like ding, ding, ding. Okay, a spot on the edge of a 0.15 meter radius disc is spinning at 33 RPMs. What can we know? Let's check it out.
You're gonna have to change the paper cover here.
We're gonna change out our disc. Careful, careful, it's an antique.
It's not that old. This is probably about 10 years old.
Let's see, give it another.
I'm
Okay.
the antique in the room. So push the button.
Okay, so start.
So there's the point on the edge.
That's actually a good way to put it. And we want to know, what can we know about this? What can we know?
Well, it's going around at 33 RPM,
Okay.
and it's a certain distance, radius from the center.
So can't we know the period?
We should be able to calculate the period.
Yeah.
Just like we did, instead of 60 revolutions, it's going to be 33. You
Yeah.
just push it in.
Okay. And once we get the period, we can also find the velocity and acceleration. And
Yeah.
our heart so desired. Should we do this?
Yeah, I just erased the 60 revs right there
Right here. This guy right there.
and make it 33.
33 revs. 33 revolutions in 1 minute. That's what we said there?
Yeah, RPM, revolutions per minute.
Oh, there it is. Yep. Okay. And what can we know? Well, again, we want to get it in seconds. We just 33 divided by 60.
It's gonna be 0.5 something.
0.55.
0.55
0.55.
revolutions per second. So that's the period. Now we could go ahead and get the velocity of that thing on the edge. We could find the acceleration, but that's boring. We've already done that. Let's not do it again.
That's old news. Okay. What is the same about every point on the disc as it spins? Oh.
That's all right.
Ready, set, bada boom. What's the same?
Well, I can see the differences. I can see different things going on.
Well, think about planetary motion, right? Aren't the planets in the center going faster than the ones way out there in the galaxy?
Yeah, they are.
Okay, so same thing here. So these ones are going faster in the middle than the ones on the outside are.
And that's because they've got a farther distance to go farther out and a less distance to go closer in.
So what's the same? Well, the period's the same.
They both go around in the same amount of time.
Revolutions per second. Bada boom.
Huh.
So what's the same about every point? They have the same period.
There's more things that are the same about them, but we'll get to that in a minute.
How could we accurately describe the motion of every point on the disc?
Every point, not just a single one. This is kind of, well, besides a period, there must be something else. Let's find out.
The unit circle! Ah! I know you guys are probably having a negative response to this, but don't worry. We're not actually going to be using the unit circle, but this is what's important. The unit circle has a 0 point, which is right here.
Yeah.
And angles are measured from it. So as we make our way around the circle, okay, we have different angles.
Yeah, I noticed they've got degrees,
And
radians.
so they've got degrees and radians.
Yeah.
And we're going to talk about, how those things are related, how those two things are related.
See, so 360 degrees is 2 pi radians. 180 degrees is pi radians.
Ooh, that's a very good point. And you might be familiar with degrees, hopefully you are by now.
Yeah.
And radians might be a little alien to you, but we need them going forward. So let's get used to them. Angles can be measured in degrees or radians, as you just saw. And 360 degrees equals 2 pi radians.
Well,
So 360 degrees right here is the same thing as 2 pi radians.
Yep.
And would you guys pause the video, make two fractions out of this?
why are you doing that? Remember, radians are just units. It's
Oh.
like degrees. So when we make calculations, the radians are just the units. Sometimes they go away.
What do we have here? 360 degrees over 2 pi radians, or 2 pi radians over 360 degrees.
Those look like conversion fractions to me.
They sure are. So let's use these. Go ahead and tell me, how can we find, well, go ahead and do this. 1 degree is how many radians? 1 radian is how many degrees?
You're going to multiply degrees by one of these fractions.
Okay, so
How do you choose which fraction?
well, whatever I give you is going to go on the bottom here. So if degrees is here, again, degrees has to go there.
So how many goes on the bottom?
Well,
360?
degrees right here, 360. You do not have to write degrees. I don't know why I did that, degrees. Like that.
It's okay.
And then on the top, we just copy what we have up here. 2 pi radians.
So 1 degree is 2 pi divided by
2
360.
pi divided by 360. And I get 0.209. I'm going to call it 0.21. 0.21. And my degrees...
Now go ahead and call it 0.219. Go
219?
ahead.
209.
Oh, is it 209?
Yeah, 209 radians. Okay?
And you guys have probably done this at some point in your mathematical history.
Yeah. So it's sort of familiar.
So 1 radian is how many degrees?
Let's see. So 1 radian is what I'm starting with. Okay, and at the bottom here, if I've got radians up top, I've got to put radians at the bottom.
Over there.
2 pi is connected to that. And on top, I've got 360 degrees. Okay, so basically this one's just 360 divided by 2 pi. And again, I don't have to put the radian in there. 2 pi, and I get 5, 6, is that right? 360, 2 pi, yeah. 565. Is that right?
That's not right. You know what? I think you need to put parentheses around that 2 pi.
Oh, you know what? I think you're right. I was like, that number doesn't seem right.
That's too big because it should be less than.
There we go. That's it. There it is.
What is it?
57.
So 1 radian is 57 degrees.
57 degrees.
You guys think you can do this? It's not hard. If you've taken chemistry, you should be good at this kind of stuff.
I'm like, we only have 360 degrees in a circle. I was like, hold on. So, all right. Oh, this is important. This relationship is important. So 1 revolution equals 360 degrees, which equals 2 pi radians. You want to show them the wheel?
Yeah, okay.
What do we mean by this? Behold, the wheel. Okay, so 1 revolution looks like this. Right there, right? Because it's blue tape's in the bottom.
That's 1 revolution, and how many degrees did that tape go? Well, it's white tape on this side. Turn the wheel around.
Oh, this way.
There's the blue tape. Actually,
Yeah.
it's kind of
now
raggedy.
360 degrees looks like this again.
360 degrees.
And 2 pi r radians looks like this again, right? So they're all the same thing, just a different name for them.
Just a different way of looking at them, and different ways are useful in different situations.
Ooh, important. This is the single-handedly most important slide in this unit.
Yeah.
The arc length S traced by a point depends on the radius r and the angle theta in radians.
Yep.
Beep, beep, right there. Write this down. This is your Rosetta Stone. This is what helps you go from linear to angular motion. Very
That's right.
important.
Yeah, you know, you can kind of demonstrate that with a wheel.
Yeah, let's take a look.
Because S would be, well,
So S can be, so this is our radius, right, from the center. Where's that blue thing at?
There it
Okay, so from the center to here, that's the radius, right?
Yeah.
And if I wanted to know the S, or the distance from here to this blue tape,
Yeah.
that takes up a certain angle.
There's an angle right there, yeah.
Right, so here's our S, here's our radius, our R, and the angle would be just the angle between those 2 points.
And the key here is you have to use radians. You can't use degrees.
Yeah, that's why radians are so important. Even
Yeah.
though we're comfortable with degrees, we
Yep.
gotta get uncomfortable.
Yep.
Comfortable with being uncomfortable. Okay.
Yep.
Until we get comfortable. Okay. So, what's our next slide? What do we have up here next? Okay. How far will a bicycle wheel of radius r equals that, 3.34 meters, roll in 1 revolution?
Okay, so let's put that equation, S equals R theta.
I think it's a good idea. Okay, S equals R theta. And we want to know how far a bicycle wheel, so that's this, right?
That's going to be that, yep.
Yeah, that's what we're trying to find. Will it roll a bicycle wheel of radius? Okay, so that's our radius. That's going to be our 0.34 meters.
Yeah.
Roll in 1 revolution. Okay, well, we said that 1 revolution equals 360 degrees, which equals 2 pi r.
And since we're using this equation, we have to use radians.
Radians. Okay, we have to use this. So how can we get there?
Well, the radius is 0.34.
Well, didn't we just say that 1 whole revolution was 360 degrees, which was 2 pi r?
Yep, so all you have to do is do r times 2 pi radians.
Yeah, we can just put that in there.
Yep.
Okay. So S equals 0.34 meters times 2 pi radians. Okay. Times 2. Oh, I should probably put that in parentheses, huh?
No, you don't need to.
Is it good?
It's for division.
Oh yeah, you're right. Okay. 0.34, 2 pi. Oh, we're good. Okay. And I get 2.1 radians. Well, let's talk about the units here. So I've got meters here and radians here.
And radians go away.
They go away.
Because the answer to the S is meters.
Because this is essentially distance,
Yeah.
right?
Yeah.
So what that means, we look over here. Okay, that means that it's that from here to here is 2.1 meters. Let's measure it.
Well, no, this is a different radius. I've got a better idea.
Oh.
Here is 1 meter. Let's measure S, because what it does, it leaves a mark on the table that's equal to S. So we need another meter stick.
Yeah, I know.
Hang on, let me grab another meter stick.
Yeah. Should I move it over a little bit, you think?
No, just leave it right there.
Okay.
And so what we have then, come here you, is 1 point, so S is, let's call it 1.59 meters. So if S, that's how far it rolls in 1 revolution.
Can we do this?
What's the radius?
Ooh, let's do it. Oh, great idea. Okay, wait. So what was the distance?
That distance was 1.59 meters.
Okay, and my theta was 1 revolution, which equals
2 pi radians.
radians. And we want to know what the radius of the wheel is. So we can just divide by this. R is going to equal 1.59 meters divided by
2 pi.
2 pi radians. Radians goes bye-bye. 1.59 divided by, parentheses, 2 pi, and I get 0.25.
0.25, and you know what? This thing appears
You got it? Is it accurate?
to be 0.25 on the nose.
Woohoo! That was cool! Hey, good job, Mr. Boykin. High five.
Boom. Ow, mommy.
Thinking on the fly. Okay.
Here's a new
this
word.
slide. Subtend. In geometry, an angle subtended by an arc, line segment, or other curve is one whose 2 rays pass through the endpoints of the arc.
So you've got 2 arcs here.
So these are the 2 rays that pass through the endpoints of the arc. And we just say that the angle subtends them. Basically,
So this
it
one is
takes up the
that
space.
was 45 degrees right here for the same circle.
And this angle is how would you say it? It
Subtends 105
it
degrees.
subtends 105 degrees. So it takes up 105 degrees.
Yeah, you're
Let's
going.
do that.
Yeah, I get you. Okay, boys and girls. Wait a minute. I got to get you where you aren't. I can actually see this thing. Okay, imagine from your eye or from the camera here to the edge, to the ends of both meter sticks. That is an angle that's subtended. What happens to that angle?
It becomes bigger, right?
That's right.
And so the angle subtends a larger amount.
Yeah.
Now it's subtending a smaller distance.
Wow! Down goes
Sorry,
blanket!
sorry. So it's subtending a very small distance. It's a smaller angle. It takes up a smaller amount of degrees. And now we're subtending a large amount.
That's right. That's all. And the word subtend is just the angle that you get from your viewpoint to the ends of that was a meter stick, that was a line segment, but it also works for arcs.
All right. How wide is your thumb at the base of the nail?
So if you have a ruler, measure that. Do it, start from 10.
Yeah, I think you're right.
What are you going to call that?
I'm going to call that maybe 0.7?
It's going to be
0.07, sorry.
see that's going to, let's see, 1 centimeter is
having a hard time.
0.01. So that's 0.01 something. 0.017?
We'll call it 1.7. Yeah.
0.017.
I can't look at all the lines.
I know.
It's hard to look at them. Okay, so
So hers is 0.017.
What's
Use whatever ruler you got. Measure how wide your thumb is at the base of the nail.
Okay. Now, held at arm's length, how far is it from your eye to your thumb?
Okay, don't put your eye out. Okay, that appears to be 0.621.
0.621. So, 0.621. Okay, so, okay, what's next? What do we do with these? What angle does the width of your thumb subtend, take up, when held at arm's length?
So S is the arc, that would be your thumb,
Okay, this is my thumb.
and R is how long your arm is. Oh, I just thought of something. If you take your thumb at arm's length, what happens to that angle as it gets closer?
Ooh, it subtends a larger angle.
Yeah.
It takes up a larger angle. Okay, so, and we have so kindly put the equation that we're using up there for you guys. But you guys know you could just divide by R. And so our S is our thumb, which is 0.017 meters, divided by our R, which is the length of our arm, which is 0.621 meters.
And the number you get is going to be in radians. That's why we're using radians.
That is why radians matter. 0.017 divided by 0.621, and I get 0.027.
0.027 radians. Now here's the thing. People with longer arms tend to have bigger thumbs. People with smaller thumbs tend to have shorter arms. So if you hold your thumb out at arm's length, you're subtending a particular angle, and it's, within human variation, it's pretty much the same for everybody.
Yeah, so it's consistently this angle.
So if you want to know the angle of something, that's called the rule of thumb.
So how can we use the rule of, I lied, we got another question here. How many degrees is that?
So we got 2 pi radians is 360 degrees. And where's our answer?
Right here, I got too many numbers on here. I'm gonna erase. Oh wait, I should probably use that.
But you can erase that,
Okay, so we're trying to get to degrees,
yeah.
right? So I'm just gonna put radians on the top here, degrees on the bottom here, degrees on the top. My radians is 2 pi r, 2 pi radians, I'm sorry, and my degrees is 360, right? Because these two things are equal to each other. And then I'm just gonna say 0.2027, look at that. Oh, wrong. 0.027. I just like to do the top row first, and then I divide
that's the way
it by.
to do it. That's the only way to do it.
That's the only way. And again, parentheses in the bottom here. 2 pi, and I get 1.5 degrees.
So that's about 1.5 degrees. So if you hold your thumb out, the angle subtends is going to be right around, well, it's between 1 and 2 degrees.
Yeah, this angle, the angle from there to there.
Do that again.
The angle from here
One
to
side.
there. That's 1.5
That's a
degrees.
very small slice of pizza.
Yeah, very small. Don't go to that place. Don't order pizza from that store.
Better be an extra large.
Okay, the moon has a diameter of that much. If it orbits that many meters from the Earth, what angle does it subtend in the sky?
So this is going to be exactly the same. Let's see, the diameter of the moon would be like the width of your thumb, wouldn't it?
Yes.
Ooh, you just erased that.
That's right. I'm like, I don't know what to keep anymore. Okay, so what did we say it was? We said the S is going to be the...
S is the diameter of the moon.
Okay, diameter. And then the R is going to be the distance, right? The
Yeah.
orbital distance.
Uh-huh.
Okay. Orbital distance. So my S is going to be 3.48 times 10 to the 6th meters. If it orbits that far away from Earth, 3.85 times 10 to the 8th meters. And this will get us the angle
Yeah,
that it
don't
subtends in the
clear your
sky.
calculator, just put that in because we're going to need what you've got in
Oh,
there.
okay. So I need that. 3.48 e to the 6th divided by 3.85 times e to the 8th, and I get 0.009. Dang, wasn't as ugly as a number as I thought it would be.
And that's going to be radians.
radians. Yeah, our meters cancel out. You see that? Okay. Can you cover the moon with your thumb?
What angle did your thumb? It's still in your
Oh,
calculator.
it was 1.5 degrees.
So you're...
It
Well,
was-
you should
point-
have-
Oh, it was 0.027. I was like, we can work backwards if we need to. It was 1.2. It was 0.027 radians.
So
degree
can
right
you
here.
cover the moon with your thumb?
Absolutely.
Yeah.
Because this is a bigger number, right?
Yep.
And if you walk outside tonight and you cover it up, you're successful in doing that.
Of course, it all
Right.
depends on the phase of the moon.
True.
When
So-
we watch this.
The new moon. There's no moon. Okay. We did this.
No, we haven't.
Oh no! How could you tell if the moon changes size from when it from when it rises to when it's overhead?
You ever notice how big the moon looks when it's rising?
Okay,
And then when
well,
it's high in the sky, it looks small?
so like we said, this angle right here is a consistent
Right.
a consistent angle.
Yep.
And we can tell if it's bigger if it changes size simply by covering it up with our thumb at that certain point.
Yep. When it first rises, so boys and girls, that would be an excellent thing to do. We're done!
We're done. Woo!
Except for...
The homework, okay. So the wheel over here, as we measured before, has a radius of 0.25 meters. How far will it go if it turns 25 times?
Oh.
If it turns through 25 radians, how far will it go? If it rolls 25 meters, A, how many radians has it turned? B, how many revolutions?
Boom, 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 boom.
Do it.
All right.
Good luck.